Alright, so here we have a gas equilibrium. You see here this SO2Cl2 gas is decomposing into sulfur dioxide and chlorine gas. And it says that a 4.32 gram sample of this liquid SO2Cl2 placed in a rigid evacuated 1.5 liter vessel, and the container is heated to 400 Kelvin. When this happens, the sample, which was a liquid, vaporizes completely and then will start to decompose. The decomposition reaction is endothermic. That's going to be important later, so they gave us a little piece of information there for later. Now, if no decomposition occurs, what would the pressure be in atmospheres in the vessel? Okay, so I'm hoping you see you got a volume here, you've got a temperature here, we're looking for pressure, we have a gram sample which we can easily turn to moles. That screams Pivnert. So let's do that. We've got 4.32 grams. We're going to turn that into moles by dividing by the molar mass of SO2Cl2. Now we have our missing piece that we can plug into Pivnert. Rearranging it, we've got our pressure is our moles times the proper R, 0.0821. I guess you could have used the 8.314 also and gotten your answer in kilopascals. Oh no, I'm sorry. It says right here in the question, see, listen to me, read in atmospheres. So that's why we're using 0.0821. Careful, because they've given us temperature in Kelvin already, so sometimes you might want to already convert it again, but it's already given to us in Kelvin, so don't add the 273. And we divide by 1.50 liters. We do good sig figs here. We've got 3 sig figs in our mass and our volume and our temperature, so that's why we have 0.701 atmospheres. Now, when the system has reached equilibrium, the total pressure in the container is 1.26. Remember, we just calculated 0.701. That is if no decomposition had occurred. And you see here, when we decompose, we are going to go from 1 mole of gas to 2 moles of gas, so we expect our pressure to increase because we're going to have more moles of gas at equilibrium. So what we want to do here is calculate the partial pressure in atmosphere of the 3 gases in the container. Alright, so equilibrium, this is calling for an ice table. So initially we have 0.701 atmospheres for our SO2Cl2. And of course initially we have none of the sulfur dioxide, none of the chlorine. And then we have our change, minus X for our reactants, plus X for our products. So here we have, you see the equilibrium line in the ice table, 0.701 minus X, and we have X and X for our products. So when you add those up, 0.701 minus X plus X plus X, you see that our total pressure is 0.701 plus X. And they gave us the total of 1.26 atmospheres. So when you do a little math here, you solve for X, and you see that X is equal to 0.56 atmospheres, and that's going to be for my sulfur dioxide and my chlorine gas. And then the 0.701 minus 0.56 gives me the 0.14 for my sulfur SO2Cl2. 0.701 minus X, so 0.701 minus the 0.56 gives me 0.14 atmospheres. Now they just made us find all these partial pressures, so you can see in the next part we're going to be doing the equilibrium constant and solving for it. So first, what is the equilibrium constant expression, Kp, for this reaction? So again, it's asking for Kp, so we want to use the partial pressures, products over reactants, so the pressure of SO2 times the pressure of Cl2 over the pressure of SO2Cl2. And now calculate the value. So we're going to plug in the pressures that we just solved for in part B. Now again, if you had no idea how to do part B, make up some answers and give three pressures. Pressures 1, 2, 3 atmospheres. Doesn't matter. Because when you come down here, you plug those numbers in, the fake numbers you gave, and you'll still get credit for solving the KP value because you used numbers from part B. But the real value, we've got 0.56 for our two product pressures and 0.14 for reactants. So you see our KP value is 2.2. Now part D. Let's say the temperature is increased to 425 K. Will the value of KP increase, decrease, or remain the same? Now this is where it was important to remember that it told us that the decomposition reaction is endothermic. Endothermic means heat going in. So heat is treated as a reactant. So poke, 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 Le Chatelier. When I add heat, I'm going to force my reaction to go to the product side. Alright, so when I poke the heat, it's going to force the reaction to go that way, away from the poking. And so according to Le Chatelier, adding heat to endothermic causes more products to form, so there's going to be more partial pressures of those gases, which are in the numerator of my KP expression, so therefore my KP is going to increase. And then our last part here, it says in another experiment, the original pressures are all 1 atmospheres at 400 Kelvin. Predict whether the amount of the SO2-Cl2 in the container is going to increase, decrease, or remain the same. So we just solved for K, and now we're going to give a new dimensions, new conditions for the gases, 1 atmospheres each. This is screaming Q. So if we solve for Q, we can compare Q and K, and then we can determine whether or not the reaction is going to be going to the right or to the left, or if it's at equilibrium. Alright, so here's everything that we need. So my KP expression, or Q expression, when I plug 1 in for everything, that means Q is equal to 1. That is less than my K value. 1 is less than 2.2. So the reaction is going to shift to the right, continue towards equilibrium. Because the reaction is going to the right, that means the amount of SO2-Cl2 is going to be decreasing, because it's going to be decomposing. Alright, I hope this helped you, and I'll see you soon.